So our speaker for today is Dmitry Zakharov, and did I pronounce that correctly? I'm sorry if I did not.
Good.
And the title is Zeta Functions on Graphs.
Okay, so I've never done this before in that I've never given a Zoom talk out of this setup. So please feel free to interrupt me if you can't hear me or if you can't see what's going on. Of course, if you have math questions, please feel free to ask me as well. Sam here? No, Sam never came. All right, so first of all, we're going to talk about zeta functions of graphs. So I'm going to begin by talking about the Riemann zeta function. Do you guys know what the Riemann zeta function is?
Yes.
Do you guys know what the Euler product formula for the Riemann zeta function is?
Mm-hmm.
Yeah. All right, well, let me write this down since this isn't going to take too much time. And if you haven't seen this before, this is a very important thing. So the Riemann zeta function is defined in the following way. So it's the sum, n equals 1 to infinity, 1 over n to the power of s. So here s is just some number, which in order for this series to converge has to be greater than 1. Right, so this is 1 plus over 2 to the s, plus 1 over 3 to the s, 1 over 4 to the s, and so on. And so what I'm going to explain is what's called the Euler product formula for this function. So here's the idea. Every integer occurs in this sum, and every integer has a unique factorization into prime numbers, right? So this, for example, is just a 1. Then I've got a 1 over 2 to the s, 1 over 3 to the s. And this here is a 1 over 2 to the s squared. Then I've got a 1 over 5 to the s, 1 over 6 to the s, which is 2 to the s times 3 to the s, and so on, right? And so then I can take this infinite sum and write it as an infinite product. So the infinite product is going to be 1 over 2 to the s, 1 over 2 to the s squared, 1 over 2 to the s cubed, and so on. And then there's going to be a term, the same series, except with 1 over 3 to the s. There will be 1 over 3 to the s, 1 over 3 to the s squared, so on. Then there's going to be 1 over 5 to the s, 1 over 5 to the s squared, and so on. Okay? So if you take this, and of course there's a lot of proving to be done here, this is a nice exercise, but if you take this times this times this, and you take all of these infinitely many sums and multiply them together, and then you try to expand, then, well, how would you do that? You would say, okay, I need to take a term from this series, a term from this series, a term from this series, and so on. And so each and every way of taking a term from here, a term from here, a term from here will produce a unique integer, right? Because integers have unique factorization. And conversely, you'll get every integer in this way exactly once, okay? But each of these terms is actually just a geometric series with a common, with a ratio 1 over p to the s, where p is a prime number. So what this is going to be is 1 over 1 minus 2, 1 over 2 to the s, 1 over 1 minus 1 over 3 to the s, 1 over 1 minus 1 to the 5 to the s, and so on. And so what the Euler product formula for the Riemann zeta function says is that this infinite sum is actually a product over p, which are now prime numbers, of 1 over 1 minus p to the power of negative s. Okay? So the Riemann zeta function is the subject of the Riemann hypothesis, which is arguably the most important unsolved problem in mathematics. And the reason why it's so important is that it contains very exact information about the distribution of prime numbers. So the zeros of the Riemann zeta function, for example, tell you something about how prime numbers are distributed, and so on. Okay, so I'm not going to talk any more about number theory. This is just something to kind of get you into the flavor of what I'll be doing. Are there any questions? And please say something, because I just want to make sure I haven't been talking to. All good?
This is good.
Yeah,
Can
you're
you
good.
guys hear me?
Yep. Mhm.
Okay, great. All right, so I'm going to erase all this. And now we're going to be talking about something completely different. Oh, hey, Sam. How's it going? Okay, so X is now going to be a graph. And this is something that you've all seen. There's nothing special about graphs. So what is a graph? A graph is just a bunch of vertices, something like this. So I'm going to denote them V of X. These are the vertices of my graph. And it's going to have some number of edges, E of X, that's the edges. So edges, we're allowed to have multiple edges between the same pair of we're allowed to have multiple edges between the same pair of vertices. We're allowed to have something like this, like that. And we're also allowed to have loops like this. So that's an edge that begins and ends in the same vertex. So just for, I'm always going to use n to denote the number of vertices, and m is going to denote the number of edges. Okay, so what I will want, instead of just edges, what I'll want is oriented edges. Oops. So an oriented edge is just an edge with a choice of an arrow, either going this way or this way along this edge, right? So this is an oriented edge. And if this is the edge, an oriented edge called E, then the edge with the opposite orientation, I'm going to denote by E with a little bar on top. Okay, and so what I'm interested in is closed paths in X. Okay, so I'm a runner. I love running. So the way I'd like to think about this is, let's say that this is my neighborhood, and I want to figure out all of the different ways I can run a certain distance in my neighborhood. Right? So for example, I can start here and then go along here. So let's call this edge E1. And maybe this edge is E2. I don't know, E3, E4, E5. And I want to end up back here, right? So this edge is going to be E6. Okay, so a closed path in X is simply a sequence of oriented edges. So example would be something like E1, E2, E3, E4. Then I'm going to go along E5. And then I'm going to go along E5 just one more time, just for the heck of it. Then I need to go back along E4. So I'm going to go E4 bar. And then I'm going to go back along E6 to the vertex that I started with. Okay, so let's try to formalize this. A closed path in X is a sequence, P, of edges, E1, E2 through En. So the EIs are oriented edges in X. And now if I have an oriented edge, it's pointing towards a certain vertex, and I'll denote that vertex T of E. That's the target vertex. And it has a certain source vertex S of E. Okay? And so I want this path to be continuous in the sense that every edge has source given by the target of the previous edge. So the source of EI plus 1 is the target of EI. Okay, and I also want my path to end up at the same vertex where I started. So the source of the first vertex, E1, is the target of En. Okay, so that's a closed path, and the length of the path, L of P, is just the number of edges. So this is the length of P. Okay, and so I'm going to pose the following question. Well, actually, hold on. There's one more definition that I need to make. So if any of you are runners, you probably know what I'm saying. When you're running, it's kind of really boring to do an edge and then run back along the same direction, okay? So I'm going to say that a path P is reduced if none of these edges are adjacent to their opposites, to the same edge with an opposite orientation. So P is reduced if EI plus 1 is not equal to EI bar for I equals 1 to n minus 1. And also, I don't want the last edge to be the opposite of the first edge. So En is not equal to E1 bar. Okay. So think about a closed reduced path is a way of taking a run or a stroll around your neighborhood with a property that you never actually turn back and go back the way that you came. Okay. All right. And so let's ask the question. How many ways are there to do a, I don't know, 3-mile run in your neighborhood or a 4-mile run? How many closed reduced paths are there of a given length? How many closed reduced paths of a given length? Can you guys see the bottom of the board? Good. Can you hear me? Great. You can hear me. Wonderful. All right. So now let's talk about this. So let's just do a quick example. Let's say that the neighborhood that I live in is a tetrahedron. So this is the complete graph on 4 vertices, and it's a tetrahedron because every edge length is going to be 1. Okay, so my graph X is K4. And so I'm going to use, I don't know, NK to denote the number of closed reduced paths of length K. So unless your graph has a loop, N1 is going to be 0, because there's no way to do a 1-mile run and end up where you started. N2 is also going to be 0, because, well, if you start at a point, you go somewhere, the only way to go back and to do a run of a 2-mile long run is to run back along the same edge, and so we're disallowing that, so N2 is always 0. N2 is also 0. What about N3? So that's more complicated, right? N3 corresponds to, there are 4 triangles in my graph, right? So I can choose to go along a triangle. There are 2 ways, 2 directions to go along any triangle. I can go like this, or I can go in the other direction. And then there are 3 choices of how to do a starting point, right? So that's going to work out to what's 24 different 3-mile runs that I can do on my tetrahedron. Okay, and so what I would want is some kind of formula for NK, right? So let's say I want to do a half marathon in my neighborhood. How many ways are there to do how many paths, closed reduced paths of length 13? Okay. So if there's one thing that I want you to take out of this lecture and remember is that if you have a problem for counting something, if you have some enumerative problem that depends on a certain index, then what you want to do is, instead of finding a formula for this index, you want to find what's called a generating function. So instead of finding MK, try to find N1 times S plus N2 times S squared plus N3 times S cubed and 4 times S to the 4, right? So if you have a function and it has a Taylor expansion at a point, that Taylor expansion has infinitely many coefficients in it. So you can roll infinitely many different coefficients that you're trying to find into a single function. And if you know that function, then you already know those coefficients, but you maybe know a lot more. If it satisfies a certain differential equation, you know how to find the coefficients recursively. Maybe there's an explicit formula for this function. So it's always a good idea when solving an enumerative problem to try to find a generating function. Okay, well, I know how this generating function works. So to get a good answer, what I'll actually do is I'll put a 1/2 here, a 1/3 here, a 1/4 here, and so on. And so I'll call this function f of s. Okay. So this is the sum from k equals 1 to infinity, nk over k, s to the power of k. Okay, and so now I'm going to do a fairly long calculation to explain how to find this function. Okay, so I'm going to erase the title because it uses up about 10% of my board. So let me leave this here and let me rewrite the definition of nk. So nk is the number of closed reduced paths of length k. All right. So there's quite a few tricks here. And first of all, well, okay, this is undergrad talk. Maybe I don't have to explain that I didn't do it. But this is, the people who developed this are Hyman Bass, Audrey Terrace, Harold Stark, Ihara. There's some quite famous mathematicians that came up with this stuff. Okay. So here's what I'm going to do. F of s is the sum from k equals 1 to infinity, nk over k, s to the power of k. Okay, so I'm going to do a following formal operation. This is the sum from k equals 1 to infinity, sk over k, times the sum over all C, which are closed, reduced paths of length k of the number 1, right? Okay, and so now, how do I know if a path is closed and reduced, right? So if I have C, which is a path E1, E2, etc., Ek, then this is closed and reduced if and only if the source of E2 is the target of E1, and E2 is not E1 bar. The source of E3 is the target of E2, and E3 is not E2 bar, and so on. Okay? So here's how I'm going to impose these conditions. I'm going to introduce a function, W, EF, which depends on two oriented edges. So these are oriented edges of my graph X. And so this function is going to measure whether or not this pair of oriented edges can occur in a closed reduced path. So it's going to be equal to 1 if the target of E is the source of F, and also E bar is not equal to F, and it's equal to 0 otherwise. Okay? And so therefore, how do I measure whether or not this path is closed? Well, what happens if, given such a path, a sequence of oriented edges, I'm going to compute the following quantity. W E1 E2, W E2 E3, etc. W EK minus 1 EK, W EK E1. So, if all of these numbers satisfy the property that my path is closed and reduced, then this is a product of a bunch of 1s, and I get a 1. Well, okay, sorry, I ran out of room here. This is a 1 if C is closed and reduced. If my path fails to meet at some point, or if it goes up and back, then the corresponding number is 0, and so I get a 0 in my product otherwise. Okay, that makes sense?
Yeah.
So therefore, this sum of ones is in fact a sum of expressions of this form. So this is a sum, k equals 1 to infinity, s to the k over k. And now I'm summing w e1 e2, w e2 e3, w ek e1. And now I can sum over all possible sequences of e1s, e2s, e3s, and so on. All sequences, e1, e2, ek. If this sequence corresponds to closed reduced path, this quantity will be 1. If it doesn't, this quantity is 0, so hence it doesn't contribute to the sum. Okay, and now here's the wonderful trick. So this W has two entries, which are oriented edges. So here's what I'm going to do. I'm just going to take a matrix. So W is going to be a 2m by 2m matrix, where m is the number of edges of X, whose entries are precisely these numbers. Okay. And so what is this quantity in terms of this matrix? Can someone tell me? Okay. What's the sum from I equals 1 to k, aii? What's that called?
Trace.
Trace, good. What if you take the sum aij, aji over all aj from 1 to k? What's that going to be? So, exercise, this is the trace of a squared. And if you take the sum aij, ajk, aki, you get the trace of a cubed, and so on. Okay? So this humongous looking sum is actually nothing else than the trace of the kth power of w. Okay? So we have a very simple formula. This is the sum, k equals 1 to infinity, s to the k over k, times the trace of w to the k. That's just some slightly advanced linear algebra. Okay, and now it gets better and better, right? So this, I have an s to the k here, which I can pull inside this trace, right? So this is the sum from k equals 1 to infinity of 1 over k trace of sw to the k. All right. And now a trace is a linear operation on matrices. So I can pull it out of my sum. I've got a 1 over k sw to the k. Now here's another question. What is the sum from k equals 1 to infinity, x to the k over k?
E to the x.
Sorry?
E to the x.
There's a k here, not a k factorial. All right, let me make it a little easier. What if there's a minus 1 to the k minus 1 here? What is that? What does that sum to? Anyone? Okay. Well, this is log of 1 plus x. And so if you remove the minus sign, then what you get is negative log of 1 negative x. Okay. So here x is a real number, And in fact, it has to be, this series converges only if x is less than 1 in absolute value. But you can also define the logarithm of a matrix by this same formula. So what this expression is the trace of the logarithm of the, well, 1, which in this case is the identity matrix, 2m by 2m identity matrix, minus SW. And there's a minus sign, which I'll pull out. Let me put it right here, like this. Okay. And so if I have a minus sign of a logarithm, I can put it as inside this as an inverse, right? So this is going to be trace log of I 2m minus SW inverted. Okay, and one last bit of advanced linear algebra that I'll have in this lecture. If you have the trace of the logarithm of a matrix, then that's the same thing as the logarithm of the determinant of the matrix. It's a nice little fact. And so, in other words, all of this is the logarithm of the determinant of I 2m minus SW inverted. And so at long last, I have a very explicit formula for my function fs, which counts closed paths of length k. All right. I want to erase most of this, but not everything. So let me move it up here. This formula. Logarithm determinant of I 2m minus SW inverse. Okay, so what is W? W is a 2m by 2m matrix. The entries of W are labeled by pairs of oriented edges in my graph, exactly like this. So what is my conclusion? My conclusion is that the function f that I was studying is maybe not the right function. Instead, I should study the function exp f of s. Okay? If I take the exponential, all I have is the determinant the inverse of the determinant of a 2m by 2m matrix. And this is called the zeta function of the graph x. It's called the Ihara zeta function of x. Okay, so maybe this is a good place to pause. Are there any questions about this? Please say something.
So you would still need to calculate W in order to
Yes,
find. Right.
But now, I mean, this is just a 2m by 2m matrix that you can calculate explicitly from a graph. And let me write down okay, in a few minutes, I'm going to give an even better formula for the zeta function of the graph. Okay, but the point is that why is this zeta function so nice? The zeta function is 1 divided by a polynomial in S of degree 2n. So this zeta function is actually a lot less mysterious than the Riemann zeta function. It's the inverse of a polynomial of degree n. So for example, it doesn't have any zeros whatsoever, right? So the Riemann, well, the Riemann hypothesis as state, if you try to state the Riemann hypothesis directly for this function, it's trivial, it has no zeros, but there is a version of the Riemann hypothesis for it. Okay, so now what I want to do is I want to find what's called an Euler product formula for this. Let me erase this. And so let's look at this function f of s again. So f of s, it's the sum of nk over k, s to the k, from 1 to infinity. And I'm just going to do a little bit of a trick, right? So this, I can do the following thing. I can say this is the sum from k equals 1. You know what? There isn't really that much time. Let me just not do this calculation. No, okay, this isn't so long. Okay, so this is a secondary calculation that I want to do. So this is the same thing as the sum over all C. So these are closed, reduced paths. And what am I summing? I'm summing S to the length of the path. And I'm dividing by the length of the path. Right? So if the length of the path is k, then this expression contributes 1, s to the k over k here. So if nk is the number of paths of length k, then that's how many contributions I have. Okay, and so I'm going to give a couple of more definitions. So I'm going to say that a path is primitive if P is not the power of any other path. Right, so one way I can do my 13-mile run is to just find a 1-mile loop and do 13 loops of it. Okay? So a primitive run is one which is not 2 or more runs repeated consecutively. Okay? And so if C is a closed reduced path, then it is a unique power of a primitive path. So instead of summing over all closed reduced paths, I can sum over all primitive paths in the following way. So this is the sum over all P, which are primitive paths. But now, instead of looking at all primitive paths, for each primitive path, I have to look at all of its powers. Right? So I'm going to take the sum from n equals 1 to infinity, 1 over L of P to the n, times S L of P to the n. Okay. So that's going to be the sum of over all P, the sum over all n from 1 to infinity, 1 over n L of P, S to the n L of P. Okay, and so I'm going to do one last little trick. I'm going to say that two primitive paths are equivalent if they only differ by a choice of starting point. Okay. So for example, the path E1, E2, E3 is equivalent to E2, E3, E1 is equivalent to E3, E1, E2. Okay. So an equivalence class of paths is a primitive way to go around my graph where I've forgotten where I started. Okay. And so definition, a prime of X is a equivalence class of primitive paths. Okay. So what are the number? So if the length of a path is n, then the number of elements in the equivalence class of P is also n. Okay, they have n different points that I could start with. So therefore, if instead of summing over primitive paths, I now sum over all P, and this is going to be the math frac P, so these are primes in the graphs, then, well, this L of P is going to go away. So I'm just going to have the sum from m equals 1 to infinity, 1 over n, s to the n L of P. Why is that? Well, because every P, every primitive path P, has exactly L of P representatives. So I'm adding 1 over L of P times. So this is going to go away. All right. And so therefore, what do I have? I have the sum over all primes of the sum from n equals 1 to infinity, 1 over n, s L of P to the n. And again, this is the Taylor series for log of 1 minus x. So what this is minus the sum over all P of log of 1 minus s L of P. And, well, the sum of logarithms is the logarithm of the product. So this is minus log product over all primes P of 1 minus s L of P. And now, instead of having a minus sign here, I might put an inverse here. Okay. And so our conclusion is that the Euler, the zeta function, this is called the Ihara zeta function of a graph, is the exponential of this, is the product over all primes of 1 minus s, length to the power of the prime, to the negative 1. Okay. So what this is the Euler product formula for the Ihara zeta function. Okay. All right. So now I actually want to calculate the zeta function for at least one graph, because otherwise this is a little dry. Okay, so let me erase everything except this formula. And let me just say a little bit of linear algebra. Gives the following result. So we're going to introduce the following matrices. Do I have them? Sorry. So this is a 2m by 2m matrix where m is the number of edges of the graph. Now, a graph, unless it's a tree, has more edges than vertices, and here we're doubling edges. So what I'm going to do is, instead of having a 2m by 2m matrix, I want to have an n by n matrix, where n is the number of vertices of x. And so I'm going to introduce the following matrices. So A is what's going to be called the adjacency matrix. So it's indexed by a pair of vertices, and AUV is the number of edges from U to V. Okay. If there are multiple edges, this can be more than one. If U equals V and there's a loop, every loop is going to count twice. So that's the adjacency matrix. And Q is going to be what's called the valency matrix. So this is a diagonal matrix whose diagonal entries are just the number of edges incoming at every vertex. So QUV is delta UV times the number of edges at U. Okay? And so a linear algebra calculation can show the following. I'm not going to do it. That if you take the zeta function of a graph, and let me go ahead and invert it right here, right? So this is the determinant of I 2m minus SW. It's equal to the following. There's going to be a 1 minus s squared to the r. I'm going to explain what this is in a second. R minus 1 times the determinant of the following matrix. In minus as plus q minus in s squared. So what is R? R is equal to m minus n. What this is the number of loops in the graph. Or this is also called the first Betti number of the graph. Okay? So this is the rank of the abelianized fundamental group of the graph. It's all the same thing. Okay. So this is the actual formula which is best suited for calculations, because for a graph, finding its adjacency matrix in Q is you just stare at the graph and you find it. So let me just do an example. So let's take the simplest kind of interesting example. This is going to be the graph xn. So I'm going to take a single vertex and a bunch of loops like that. So I'm counting the number of ways of running in a bunch of paths like so, right? So that's accomplished by the zeta function. So let's find what the zeta function is. Well, so there's a single vertex, V. So what is the adjacency of V with itself?
4.
Well, it's 2 times the number of loops. So M is the number of loops. So each loop counts twice, right? Once for incoming, once for outgoing. Okay. And so the matrix Q, VV, the valency matrix, is also 2M. Well, I guess I should write something like this. Okay. And so therefore, if we compute the zeta function, what we're going to get is 1 minus s squared. Now, the number of loops in the graph is, well, the number of loops in the graph. So that's going to be equal to m minus 1 times, well, I'm going to have 1 minus 2ms plus 2m minus 1 times s squared. And so if you factor this a little bit, you get 1 minus s squared to the m minus 1, 1 minus s, times 1 minus 2m minus 1 times s. Okay. So let's do a slightly bigger example. Let's take the graph four. So that's the tetrahedron graph. So what is the adjacency matrix for this graph? Well, the adjacency matrix is that no vertex has a loop, so it has zeros along the diagonal. And every vertex is adjacent to every other vertex exactly once. So it's going to look like this. And what is the valency matrix? Well, every vertex has valency 3, so this is just 3 times the identity matrix I formed. Okay? And so now, if you want to do this on your own, you can calculate that the zeta function, K4, is 1 minus s squared squared, 1 minus s, 1 minus 2s, 1 plus s plus 2s squared cubed. Okay, so that's homework to do this. All right, so that's an example of a zeta function. Now, a question you might be asking yourself is, what is all this for? What can the zeta function tell you about a graph? So, what does zeta x of s tell about x? Well, if you remember the Riemann zeta function, the Riemann zeta function has a simple pole at s equals 1, right? Because the harmonic series diverges. What about the, I just erased the formula, unfortunately, right? So zeta x of s inverse is 1 minus s squared to the r minus 1, determinant in minus as plus q minus in s squared. So what happens if you plug s equals 1 into this formula? Well, I've got 1 minus s to the power of r minus 1. So this term has a 0 of order r minus 1. So the zeta function is going to have a pole of order at least r minus 1. However, this is a little bit more subtle. If you plug s equals 1 into this determinant, then this in is going to cancel this in, and you get the determinant of q minus a. So if x is a graph, what is the determinant of q minus a? So if a professor asks you a very vague question and you have no idea how to answer it right away, the answer is always either 0 or 1, okay? And in fact, it's 0 if the quantity has dimension and 1 if it's dimensionless. So this is always equal to 0. This is what's called, the matrix Q minus A is what's called the graph appellation. Graph, and it's just a classical theorem that the graph appellation, well, in fact, if you just add the sum of the, this is actually very easy to explain. If you take all of the rows of Q minus A and add them together, then all of the contributions of Q are going to cancel exactly the contributions of A. You're going to get 0. So the rows of this matrix are linearly dependent, so therefore the determinant is 0. Okay, so at s equals 1, this thing has a 0 of order r minus 1. This thing has a 0 of order at least 1. In fact, its 0 is, it has a 0 of order exactly 1. So the zeta function has a pole of order r. Its inverse has a pole of order, has a 0 of order r. Okay. And so I'm going to write down a formula, which is called, just for the benefit of Sam, I don't know if he's still here, the tropical class number formula. So I have a function. It has a 0 of order r at s equals 1. First of all, let's write this down. Zeta x s inverse has a 0 of order r at s equals 1, where r is the first steady number of the graph. You can ask, what is the first, what is the leading non-zero Taylor coefficient? And so the answer is that zeta x s inverse has the following Taylor coefficient. So it's equal to -1 to the r plus 1, 2 to the r minus 1, times a quantity called k of x, times s minus 1 to the r, plus o of s minus 1 to the r plus 1. Okay? And so what this k of x is, I'm going to have to move maybe up here. K of x is called the complexity of x. And so the complexity of a graph, it has many different manifestations. And one of them is that this is simply the number of the spanning trees of x. Okay? So you can recover the number of the spanning trees of a graph by looking at its zeta function, by looking at the first non-zero Taylor coefficient of its inverse at s equals 1. Okay, but why is this called the tropical class number formula? So the number of spanning trees of a graph is the number of elements in what's called the discrete Jacobian of the graph x. So the zeta function records the order of the discrete Jacobian. And the similarity here is with number theory. So the Riemann zeta function generalizes to what's called the Dedekind zeta function, which is defined for a number field. And the Dedekind zeta function of a number field records the class number of that number field in its expansion at s equals 1. And so the analogous theorem for graphs is that the zeta function of a graph records the order of the discrete Jacobian, and the discrete Jacobian is the graph-theoretic analog of the class group of a number field. Okay, so that's slightly advanced material. All right, so maybe let's just check this formula for K4. I've got, what, 5 more minutes, right? Yep.
10 minutes.
How much?
10.
10, okay, I can't hear you. There you go. Let's just see what happens if you plug s equals 1 into this formula. I'm curious. Okay, so zeta k4 of s inverse. So I've got a 1 minus s cubed times a 1 plus s squared times a 1 minus 2s times a 1 plus s plus 2s squared cubed. Okay. Well, anyway, let me not do this calculation. I want to do one more thing. Just check by yourselves that the complexity of K4 is going to be, I forgot what it is. Let me just mulligan that calculation. Okay, so there's one more thing I wanted to talk about very quickly. So let's look at a slightly bigger graph. And this graph is going to be the cube. Okay? And so let's compute the zeta function of the cube. Well, the matrix Q is not hard. Every vertex is trivalent, so this is will be 3 times I8. The matrix A is a little bit more annoying, right? So there's some calculations that you have to do. Now, let me just tell you what the answer is. 1 minus s squared to the 5. 1 minus 4s squared. 1 plus s plus 2s squared cubed. 1 minus s plus 2s squared cubed. Okay. And so if you stare at this for a little while and you squint, what you see is that the inverse of the zeta function of the tetrahedron divides the inverse of the zeta function of the cube, right? This divides this, this divides this, this divides this, okay? So why is that? Well, so here's what I'm going to do. I'm going to take this cube, C, and I'm going to take the group of order 2, Z mod 2Z, and allow it to act on this cube. So I'm going to take C. And so what I'm going to do with a cube, I'm going to fix a, let me draw this here a little bit bigger. Oops. I'm going to fix an axis like so. And I'm going to rotate around this axis by pi. Okay? So I'm going to take my cube and I'm going to rotate it. And so what happens if I take the quotient of the cube by this rotation? What graph do I get? So this vertex gets identified with this vertex gets identified with this vertex. So I'm going to have two vertices up here. This vertex gets identified with this one gets identified with this one. I have two vertices down here. And then, well, anyway, what I want you to check is that the resulting graph is actually the tetrahedron graph, okay? So this is C, this is K4, and K4 is the quotient of C by the action of the group Z mod 2Z, right? So in other words, there's a map from C to K4, and this is what's called the Galois cover of graphs. Okay. And then there's a theorem due to Terrace and Stark, or I guess Stark and Terrace is the right way to write this, is that if you have x prime to x is a Galois cover of graphs, then the zeta function of the target graph divides the zeta function of the source. Okay. So again, the corresponding statement in number theory, which is if you have a Galois extension of number fields, does the zeta function, the Dedekind zeta function of the smaller field divide the Dedekind zeta function of the larger field, is actually one of the starting points. A major open problem. This is called Dura-Ace Conjecture, and is, if we ever, Langland's program is like the string theory of mathematics. It's the hardest part of mathematics. The smartest people work on it. And well, one of the questions that they ask is whether or not the Dura-Ace conjecture would follow from the Dedekind conjecture would follow from some very strong results in Langland's theory. For leave a few for questions.
Okay, thank you. Are there any questions?
What is the Jacobian of a graph?
Oh, okay. That's a very good one. Do you know what the Jacobian of a Riemann surface is by any chance?
Yeah.
No.
Okay. Well, so I guess I could answer this in a couple of minutes. So if X is a graph, then I can look at the free abelian group on the vertices of the graph. And this is called the divisor group of X. Z to the V of G to the V of X. This is the free abelian group on the vertices of X. Right? So an element here is just a formal linear combination. Are the vertices and the AV are integers. Okay. And so we define two divisors to be linearly equivalent. if they differ by what are called chip firing moves. And so, well, let me just kind of draw a picture. So let's say that you have a divisor on K4, which looks like this. I don't know, maybe there's a 2 here, a 3 here, a 5 here, and a -1 here. Then a chip firing move looks like this. You take this vertex, and you think of there being a stack of 5 chips at this vertex. And at a single move, you give each of the neighbors of this vertex a single chip. So what you'll get is this. There's going to be a 3 here, a 4 here, a 0 here, and now this one's a 2. Okay? And so the equivalence relation generated by these moves is an equivalence relation on the divisor group. You can see it easily that it preserves the group operation. So there's a quotient group, which is called the Picard group, modulo equivalence. And then finally, chip firing preserves the total number of chips that you have. So on the divisor group, you have the degree map. And you have pic 0 of x, which is the set of degree 0 divisors modulo equivalence. And this is called the discrete Jacobian of x. So if you know what Riemann surfaces are, this should have been very, very familiar. If you don't know what Riemann surfaces are, when you study Riemann surfaces, try to remember this. I think the great thing about tropical geometry is that it's easier than algebraic geometry. And so I think in the far future, people are going to be learning this before they actually learn what Riemann surfaces are, just because it's so much easier to learn. So does that answer your question?
Yeah, so it's a group.
It's a finite group associated to any graph.
Thank you.
So is the Jacobian supposed to have some sort of geometric structure?
So yes, edge lengths instead of just having edge length 1 everywhere. And in that case, if you have a graph of genus G, that is to say its first Bettian number of G, the Jacobian is a real torus of dimension G. Whereas you might know that the Jacobian of a Riemann surface of genus G is a complex torus of complex dimension G. And it's what's called a principally polarized real torus, so it has an intersection form, it has a volume. Yeah, very much so.
Okay, are there any other questions? Okay, thank you very much for the talk.
Thanks. Thank you for coming.
Thank you.
Okay, well, it was nice meeting you guys.
Yeah, thank you very much.
I have one more question. One more question. Do you have any resources for learning about this? I know Brandon gave you one, but do you have any suggestions?
Okay, so are you interested in zeta functions or are you interested in Jacobians?
I'm interested in zeta functions.
Okay, because I'm, so for zeta functions, there's a very nice book by Audrey Terrace and Harold Stark. This is the same Harold Stark who won the Fields Medal for the class number 1 problem. So it's called something like this is related to a lot of stuff. This is related to number theory, but this is also related to random walks on graphs. This is related to, yeah, there's a lot of stuff that kind of happens at the intersection. So this is a really nice book, and I think it's only a few years old. It's like 2012, along those lines. Yeah. So I think that's
Thank
a
you.
really good place to start.
Great, thank you.
All right. Well, should I say goodbye?
Yes. So yeah, the meeting. I mean, people can